in the Department of Statistics at Baba Saheb Bhimrao Ambedkar Central University, Lucknow. And he has teaching and research experience more than 10 years, having the expertise in sampling theory, operational research, regression analysis, and currently he is working in the area of disease modeling. So he has more than 100 Scopus Index research articles, which is a landmark in the area of statistics. So thank you so much, sir, for being with us. Thanks to all the for your efforts and valuable time which you have given to our participants. Please unmute yourself.
Okay, thank you, Dr. Yadav. So, first of all, I must thank to the organizing institution and the whole team of the
Sir, please unmute yourself.
Yeah.
Sir.
Am I audible now?
Yes.
So thanks to the institution and the whole team, Dr. Yadav, along with the entire team, that they have organized such a very beautiful workshop, and they have given me opportunity to express my view regarding the assigned topic. So today we will be discussing the cluster analysis, and we will be doing hands-on on SPSS. So let me share the screen. We'll be discussing first theory, and then we'll be doing hands-on on SPSS. Is it visible?
Yes, sir.
Okay. So first, the thing which comes into the mind, and we should know what is the problem in hand. That is, what is cluster analysis? As the name suggests, that we have something group of objects. So cluster analysis is nothing but it is a group of multivariate techniques whose primary purpose is to group objects. We have to make the clusters. That is, respondents, these objects may be respondents, may be products or other entities based on the characteristics they possess. So later on, we will be comparing it with to the principal component analysis, PCA. That is the technique of factor analysis. So how it is different from factor analysis? And we can say that it is complementary part of that factor analysis or PCSA. So it is a means of grouping records based upon attributes that makes them similar. If plotted geometrically, the objects within the cluster will be close together, while the distance between the clusters will be further apart. So what we do here in cluster analysis, we group the similar objects on the basis of all characteristics for the comparison, all characteristics of the objects under consideration. So see, there are two things. We have several objects and we have several characteristics of the objects. If we are grouping the characteristics on the basis of their similarity, then this technique is known as PCA. There we reduce the dimension of the objects under consideration or variable under consideration or characteristics under consideration. Similar characteristics are grouped in one and we name it as first component. So this way we make other components. So there we reduce the dimensionality of the data. But here what we do, we group the objects. There we group the characteristics. But in cluster analysis, we group the objects on the basis of the all characteristics. So similar objects are put together to make a cluster. So here we will be doing that. So what is cluster variate? The cluster variate represents a mathematical representation of the selected set of variables which compares the object similarity. What are the selected variables? The different characteristics of the objects under consideration. So on the basis of all characteristics in hand, we put the most similar objects together to make cluster. See here how the cluster and factor analysis work, and here is a comparative chart that cluster analysis versus factor analysis. These are some facts about the two. The cluster analysis, here we group the objects based on the distance, that is proximity. And here in factor analysis, what we do, group the characteristics based on the patterns of the variation, that is correlation. So the basis for the similarity for the factor analysis is the correlation, while the basis for the similarity for the cluster analysis is the distance, that is proximity. So factor analysis, we form group of variables based on the several people's responses to those variables. We have different responses on the different variables, and we put similar responses together on different variables. So there we try to find the similar variables. Say we ask two questions to say respondents that what is your name and by which name your father called you. So these two questions are very close to each other, very similar to each other. So this way, the both will be put in one factor and component, and so definitely it is going to reduce one dimension at least. And if there are other similar variables, then it will further reduce the dimension of the data. And in contrast to cluster analysis, we group people or objects based on their responses to several variables. Say here, we have several variable objects and several variables. So first we try to reduce the dimensionality or dimension of these variables which are similar. Suppose we have reduced these 5 variables into in 3. Now it is 3 dimensional because these two questions are, say, variables are similar and these two are similar and this is different. So now it is and suppose we have 5 characteristics, and now on the basis of all 5 characteristics we apply these 5 characteristics to this object, to this object, to this object. On the basis of all 5 characteristics, which objects are similar, so this way we will make the clusters. Similar objects are put together on the basis of the whole characteristics under consideration. So this is the difference between factor analysis and the cluster analysis. Now, how it is different from discriminant analysis? So in cluster analysis, you don't know who or what belongs to which, and not even the number of group. Even we don't know the number of clusters, how many clusters, and how we are going to make the clusters. But in discriminant analysis, we already know the different classes, or say we classify already. We have set rules, we have and on the basis of that say variables, we have to classify only the objects in well-defined different groups or say classes. So discriminant analysis requires you to know the group membership for the cases used to derive classification rules. So on the basis of the classification rule, only well-defined classification rule, we classify the objects to different classes. So this is little bit different from this cluster analysis. We group the objects on the basis of the all characteristics, and in discriminant analysis, what we do, we have set rules. On the basis of that, we classify the different objects in different groups. It means we have in advance the number of clusters already known in discriminant analysis, while in cluster analysis, we don't know the number of clusters, how many clusters will be formed. We see on the basis of the similarity among the objects under consideration. These are some applications of this cluster analysis where this cluster analysis is applied, say in the field of psychiatry. So we have so many, say, characteristics, and on the basis of their characteristics, we classify the patients in different categories. Or the, say, similar types of the patients having the similar type of symptoms are put together to make cluster, so that a doctor may decide which treatment should be given to the which group. So the similar patients are put together in one group. So this way, this cluster analysis is applied to psychiatry, and in biology, it is used to find the group of genes. So on the basis of their gene expression, or say functions of the genes, we can classify them into different clusters on the basis of the similarity of their functions. And in information retrieval, obviously, the World Wide Web, WWW, we know it consists of billions of web pages, and on the basis of what we search, on the basis of that, the similar results are grouped together one by one, so that it is very easy for us to search the very close information on this world website. So clustering can be used to group these search results into a small number of clusters, each of which captures a particular aspect of the query. So on the basis of query, you will see the similar questions are arranged in a chronological order. And so this way we can apply this cluster analysis in, information retrieval and in this World Wide Web. How it is used in climate. So understanding the Earth's climate requires finding patterns. So similar patterns are to put together on the basis of different characteristics for say climate change, or say, to know the weather, say in the atmosphere and ocean. So to that end, cluster analysis has been applied to find patterns in the atmospheric pressure of polar regions and areas of ocean that have a significant impact on the land climate. So we have different say characteristics regarding say climate, or say this season. Then we can apply, and we can put that similar say conditions. We can find similar on the basis of all characteristics. These are similar, so we can group them. So we can apply different on say polar regions or different regions. We can apply on the basis of different characteristics. We can make the clusters. Now this is the common role of cluster analysis, that in data reduction, as the factor analysis do. So cluster analysis is also used in data reduction, or say dimension reduction. A researcher may be faced with a large number of observations that can be meaningless unless classified into manageable groups. So cluster analysis can perform this data reduction procedure objectively by reducing into different groups. On the basis of the characteristic, we can make the groups, and then we can easily analyze it. From an entire population to a sample to information about a specific group, we can make different groups on the basis of the characteristics. And how it is used in hypothesis generation. So cluster analysis is also useful when a researcher wishes to develop different hypotheses concerning to the nature of the data, or to examine previously stated hypothesis. So we have data on different characteristics. On the basis of that, we can classify to which hypothesis is very close, or which hypothesis is governed by this data. So we can make this way, we can cluster them on the using this cluster analysis. So if there are some pros, then there are some cons as well. So there are some of the drawbacks of this cluster analysis. That most common criticism with the cluster analysis is that cluster analysis is descriptive atheoretical and non-inferential. Because most of the time academicians or people used to say that this is descriptive, there is no, basis of the say theoretical, there is no theoretical ground of that of making the cluster. So this way sometimes it is known as it is atheoretical, and so that we can not have a very good inference from this analysis. So cluster analysis has no statistical basis upon which to draw inference from a sample to a population, as we do in say classical inference or say Bayesian inference or in decision theoretical inference. So there is criticism with this cluster analysis, and many contend that it is only an exploratory technique, because we have we explore the things on the basis of the characteristics. There is no some theoretical ground or mathematical ground that on the basis of that we can classify, as we do in cluster analysis, as we do in say classification in discriminant analysis. So that is why there is some criticism with this one. It is atheoretical, that it has it do not have some statistical ground, solid ground, that on the basis of that we can classify the objects in different clusters. So cluster analysis will always create clusters regardless of actual existence of any structure in the data. Suppose the data has some structure, but even then we can make different clusters. Even if we wish to make some say 4 cluster, then it will make 4 cluster. If we wish to make 5 cluster, it will make 5 clusters. But the data is making actually there are actually 3 clusters, but we can make 4 5. So that is why it faces some criticism. The cluster solution is not generalizable, because on the basis we are making sometimes some units are also misclassified, or we are making some further we are classifying. We are making, say there is a requirement of 3 clusters, we are making 4 clusters, or we are making 2 clusters. So how can we generalize the result? So it is totally dependent upon the variables used as the basis for the similarity measure. This is very important. Another very important feature, that how many features or how many variables you are going to include into the data. If you are making the inferences or making classification or cluster on the basis of say 10 variables, then you will have some different result. And if you have included some more variables or you have deleted some variables, then you will have some different solution. So we cannot generalize it. So this is the problem with the cluster analysis. Now, what is the objective of the cluster analysis? So the main objective is to group the observations, group the objects basically. So cluster analysis used for taxonomy description, data simplification, relationship identification. What is the relationship between two? So these are some, objective of the cluster analysis. Theoretical, conceptual, and practical consideration must be observed when selecting clustering variables for cluster analysis, because that is why it is said that it is atheoretical. So we have to keep in mind all aspects which can affect the classification or say clustering. So we should take care of all the variables which are impacting the results, that they must be included into the analysis. And definitely if there are some patterns or some practical considerations, they must be included into the analysis while making the cluster analysis. So only variables that relate specifically to the objectives of the cluster analysis are included. Some say spurious variables are not included into the analysis. So variables selected characterize the individual objects being clustered, because they characterize the objects on the basis of these characteristics only. So all relevant variables should be included into the analysis. How does cluster analysis work? Sorry. The primary objective of the cluster analysis is to define the structure of the data by placing the most similar observations into groups. There we classify in factor analysis the similarity. We see similarity among the variables or characteristics. Here we see the similarity among the units on the basis of the all characteristics. So to accomplish this task, we must address three basic questions. There are three basic questions we should apply on the objects to while doing this cluster analysis. That how do we measure similarity? What is the basis? What is the measure of similarity? That is, which distance function you are going to use for the cluster analysis. So the first question is, how do we measure similarity? So there is proximity matrix or proximity we apply, that is distance measure. So which distance measure you are going to apply? And the second question is that how do we form clusters? What is the basis of forming the clusters? How you are making the clusters? So we'll be discussing that there are two methods for a hierarchical cluster analysis, that either we will use agglomerative method or we use divisive method. So what is the basis for that, making the cluster? How do we form the clusters? And the third question is, how many groups do we form? How many clusters should we form? This is very important. How many clusters do we form? So one by one, we will be discussing these three questions. Basically, we should keep in mind that these three basic questions, and on the basis of that, we will be perfectly applying this clusters. One, which measure you are applying. Second, how you are going to make the clusters. And third, how many clusters you are going to make. So these three clusters we will be discussing one by one. Let me okay. So now we will be discussing different measures of similarity. Here basically we use the distance measure, and how many distance measures we will be discussing one by one. There are so many, distance measures. So, okay. So basically the similarity measures are of two types, which we have discussed, that one is correlation measure and another one is distance measure. So similarity represents the degree of correspondence among objects across all of the characteristics used in the analysis. These are the degree of correspondence among the objects across all the characteristics. So we are using all the characteristics over all the objects under consideration. So it is a set of rules that serve as criteria for grouping or separating items. So one measure is that correlational measure, less frequently used in cluster analysis, but very much used in factor analysis, where large values of R, that is correlation coefficient, to indicate similarity. High correlation indicates close similarity, high similarity. And another one is distance measure, that is most often used in cluster analysis as a measure of similarity, with higher values representing greater dissimilarity. High distance means higher dissimilarity, and low distance, lesser distance means higher similarity, greater dissimilarity. So distance between cases, not similarity. So larger difference, higher difference, so higher dissimilarity. See, this figure is telling a lot. Why we use this, I mean, distance measure in cluster analysis, why we don't use this, I mean, correlation distance in case of cluster analysis. See here, the two graphs, we have graph 1 and graph 2. See, there are 4 points and we have the pattern. So similar patterns are there. We have the in both the pattern, both the graphs, the correlation is 1, perfect. Corresponding to every point, there is another point. So the another this, I mean, second curve is say the copy of the first one, will almost similar. And similar pattern is here. So correlation is same, and that is 1, perfect correlation. But you see, to every corresponding original say points, there are points in the curve, and the distance between the points corresponding to every point is lesser in this graph 1 in comparison to graph 2. So this is highly distant. See, from 1 to 4, it is, I mean, 3 unit distant from this point, and while it is 1 unit distant from this point. So this way we can see that the similarity in terms of, since we take the distance is the measure for the cluster, a higher distance tells about, shows that the higher dissimilarity. So if we apply this one, while the correlation is 1, so we may have a larger distance. So that is why we apply the proximity or distance as the measure of similarity in case of cluster analysis. So both the graph have the same r equal to 1, which implies to have a same pattern, but the distance are not equal. Here it is only 1 unit, while it is here it is 3 unit. Now we come to distance measure. So it is very clear that we are going to use the cluster analysis, distance measure in cluster analysis. So now we will discuss different cluster distance measures. So several distance measures are available, each with a specific characteristic. The first one is say Euclidean distance, the most commonly recognized to as straight line distance. So here the distance between the 2 points say B and C is nothing but we have 2 characteristics x and y. So it is square root of xb minus xc. There are 2 points xb minus xc square plus yb minus yc. So the distance between the 2 points for the characteristic 1 and square of that, and the distance between the 2 points for the characteristic 2 and square of that, and so on if we are having more than 2 characteristics. Now squared Euclidean space is nothing but it is square of that. So remove this square root. So it will be xb minus xc square plus yb minus yc. Now we come to city block or Manhattan distance. This is also a Euclidean distance. It uses the sum of the variables absolute differences. So what we do, we take the absolute differences, that xb minus xc, there is mod of that. So absolute difference will make the negative sign as the positive. Now Chebyshev distance is the maximum of the absolute differences in the clustering variable values. So here we take the absolute differences, what we do in this Manhattan distance, and we take the maximum of that distances. If we have more than say points, 2 points, say 3, 4 and more than 4 points, then we will take the maximum of the distance, this absolute difference among the different characteristics under consideration. Now we come to Mahalanobis d square distance is a generalized distance measure that accounts for correlation among variables in a way that weights each variable equally. Here we apply equal weight to every characteristic, and on the basis of that we apply this Mahalanobis d square. Now we come to the illustration through graph that we can have the distance between these two is the Euclidean distance, and this is Manhattan, this to this absolute, and then come to Chebyshev, then we can have on the basis of the maximum of the two. So this way we can apply these distance measures to the problems under consideration. Now we'll elaborate it with one example. Say, suppose a marketing researcher wishes to determine market segments in a community based on patterns of loyalty to brands and stores. Loyalty to brand and loyalty to stores. A small sample of 7 respondents is selected as a pilot test of how cluster analysis is applied. So two measures of loyalty, that is V1 and V2, store loyalty and brand loyalty. There are two measures. Were measured for each respondent. We have 7 respondents on the 10-point Likert scale. So we have these 7 respondent A, B, C, D, E, F, G, and we have two characteristics, say V1 and V2. That is store loyalty. V1 is store loyalty, and another one is brand loyalty. We have these two characteristics, and we have 7 objects. Now we have to classify these 7 objects in different clusters on the basis of these two characteristics: brand loyalty, store loyalty, and brand loyalty. So here we have these data that it is 3 out of 10, and 4, 4, 2, 6, 7, 6, and 2, 5, 7, 7, 6, 7, 4. So these are the points you see similarity. This is the scatter plot. So this is across the characteristics. So it is V1 and it is V2. So on V1, V2, if we see that it is 3 and 2 for characteristic A. 3 on V1 and 2 on V2. So now see 3 points on V1 and 2 points on V2. So you will join this. So you will get A. So similarly, 5 points on say V2 and 4 points on 4, 5. So here we have 4, 5. Then 5, 4, 7, 4, 2, 7, 6, 6. So each 6, 6. You can see here. E 6. Here it is 6 and here it is 6. So this way we can plot this scatter diagram. And now we calculate the Euclidean distance. So Euclidean distance, we know we take the differences of the same characteristics on the 2 points, and we take the squares of that and we sum them and take the square root of that. So how do we measure similarity? Proximity matrix of Euclidean distance between observations. So we have 7 observations, 1, 2, 3, 4, 5, 6. That is A, B, C, D, E, F, G. And here A, B, C, D, E, F, G. So distance between A and A is 0. So it is dot. Now distance between A and B, how it is 3.162. So what we will do, that come to this. We are finding the distances on the characteristics for the same point. So we will see we have 2 characteristics, that is 3 and this, on the basis of these characteristics. So if we are finding this say this is x1 and this is x2 characteristics, say, so we are finding the distance between A and B. So we have point, this is x1. So or say x v1 A is 3 and v1 B is 4. So we'll take the difference 3 minus 4. And for V2 A is 2 and V2 B is 5. So we'll take the difference 2 minus 5 or 5 minus 2, whichever, and take the square and then get it square root. So here V1 A minus V1 B is square root of that plus V2 A minus V2 B square root of that. So 3 minus 4 square and 2 minus 5 square. So we have found this one 3.16. So for all characteristics, we have take the difference of the points. So here we have 2 points A and B, and we will take the difference for the characteristic 1, that is V1. Now, and for another characteristic V2, and if we have more characteristic, then we can find as we'll say V3A minus V3B square. So like that, we can find the distance. So this is calculated in through this formula. So this is distance between B and B is 0, and B and C it is 2. B and D it is 2.8. So this way we can calculate for all the objects for over the characteristics. Here we have two characteristics, that is brand loyalty and the another one is store loyalty. So first one is store loyalty and another one is brand loyalty. Now, how do we form clusters? This is very important. So simple rule is that identify the two most similar closest observations first and put them together. Then the third one, which is more closer to that cluster. Now it is cluster if we have two units. And then we will add one by one on the basis of the distance. So identify the two most similar or closest observations not already in the same cluster and combine them. Then we apply this rule repeatedly to generate a number of cluster solutions, starting with each observation as its own cluster, single observation cluster, and then combine two clusters at a time until all observations are in a single cluster. This process is called as hierarchical procedure because it moves in a stepwise fashion to form an entire range of cluster solutions. It is also an agglomerative method because clusters are formed by combining existing clusters. So this method, this hierarchical cluster or agglomerative method, what we do here, we make many to one. While in divisive method, we make one to many. From one to many, that is divisive method. Here, single observation or single unit is considered as a cluster, and we add these clusters on the basis of the similarity, closest distance. So we make the one cluster through many clusters. And in divisive, we make many clusters through one cluster. See here, from that example, we can see here, these are the initial minimum distance unclustered observations. These are 6 observations. So first observation is having 0 from its own. So from A to A it is 0. So this distance is 0, and then from A to B, A to C, A to E, A to D, this way, and B to C. So we can see it this way. Now this is the initial distance. Now we try to add the similar type of objects having the similar distance or lesser distance. So here we can see that in step 1, 2, 3, and 4, OSM does not change. OSM means this overall similarity measure. So here first E and F are added in step 1. Why? It is having a least distance, that is 1.4. You can see from this step. This one is the least distance, and it is between E and F. So at first step, we will add E to F. Then the larger distance in comparison to this 1.4 is second largest one, smallest is this one, 2. So we can add this C or B, or we can add B to C having distance 2 and C to D. So this way we can add both. See here. These having 2 distance. C to D and E to G. These 2 clusters are added. So this way B to C. This way we add, and then by one, we will add these clusters now to each other. At step, next step, this is first step, second, third, fourth. Now, these are the number of clusters. So you can see here, we have first 6 clusters because we have added this one only. Then we have added this, say G, R, A with this E and F. So let us see at which indicates that we are forming other clusters with essentially the same heterogeneity of the existing cluster. Now, when we get to step 5, we see a large increase. This indicates that joining cluster BCD and EFG resulted a single cluster that was marked less homogeneous. So here we can add at next step that this EF, we have added it at first. Then we can add another cluster having the distance very close to this one, this 1.4, that is 2. So we can add this at that step. So this way we can, here there are 6 clusters, then another we add next one, EF with G at next step, then it is 5. So G is very similar to E and F, as we can see from this. G is having distance 2. So this way we can add. Then we have made 4, then we have made 3, then we have made 2, and at last we have made the single cluster. But see here, the overall similarity measure is not changing drastically, but here it is changed drastically at second stage. It is 2.8, almost 3, and 3. So this way we can have idea that there must be 2 clusters, one having these 2 and distances, and another having these. So this way we can make the clusters. How many group do we form? This is the another question. So there are 3 cluster solutions of step 4. Teams the most appropriate for a final cluster solution with 2 equally sized BCD and EFG and a single outlying observation A. So A is outlier type observation, you can see here. A is, these 3 are similar to each other, these 3 are similar to each other, and but this is distant from. So this way we can make 3 clusters, one having these 3 observations, another having these 3 observations, and this is distant from these 2. So we can put it as a single cluster, and so we can make 3 clusters this way. This approach is particularly useful in identifying outliers such as observation A. It also depicts the relative size of varying clusters. How many clusters should be found? Although it becomes unwieldy when the number of observations increases. So it does not work very well if we increase the number of observations. See, here at step 1 we have added E to F. Then at step 3 we have added this G to this cluster. So we have made this cluster having 3 observations. Now see, C and D are having similar very small distance. So we have added at step 3 C to D. Then step 4 B is close to that. So we have added that. So now these are having there are 2 clusters. Say this big one having 3 observations and these 3 observations. Now they are having the distance lesser in comparison to A. So we will add at next level these 2 clusters. So now that the cluster will have 6 observations, and at last step the last one will be added. So this way we can make the clusters. See here, this graph is known as dendrogram. We use it for description of the agglomerative method as well as division method, both. So what is dendrogram? Graphical representation or tree graph of the results of a hierarchical procedure, starting with each object as a separate cluster. See here, A, B, C, D, E, F, G. All are single valued cluster, single observation clusters. And then we combine them on the basis of the distance. So this shows graphically how the clusters are combined at each step of the procedure until all are contained in a single cluster. So see, at first step, what we have done? We have added E to F. Then this cluster has been added with the G at second step. Then at third step, we have added C to D. And at fourth, it is added to with P. And now these three, B, C, D and E, F, G, these are added to each other at fifth step. Now this outlier is added at the sixth step to make a single cluster. So this is from many to one. And if we have added all together, then we separate one by one on the basis of the high distance. So first A will be separated because it is having highest distance among these observations. That is known as divisive method. So outlier remove or retain on the basis of the importance of that. Either if it is not of importance, it is not important, we may remove it. And if it is important, then we should contain it. We should retain it. So outliers can severely distort the representativeness of the result if they appear as structure cluster inconsistent with the objective. If they are not consistent with the objective, then definitely they are going to, I mean, hammer the analysis. They should be removed. See here, clearly it is written that they should be removed if the outliers represents aberrant observation not representative of the population. Observations of small or insignificant segments within the population and of no interest to the research objectives. So if they are overall in single word, we can say if they are not important, we can remove them. But if they are important, then we will have to retain them into the analysis. So they should be retained. If a undersampling or poor representation of the relevant groups in the population are there, the sample should be augmented to assure representativeness of these groups. Suppose that type of observation is present in the population and we have taken a single one, say. So what we do, and we used to say in sampling theory that sample should be well representative of the population. So it is very important that all type of representations, all type of objects are variables, observations or units should be into the sample from the population to represent that population. So sample should be chosen in such a way that it must be well representative of the population. If it is not so, then we are going to have a biased result. So what we do? We increase the sample size. How to detect outliers? So that method is also useful. We make the clusters. So outliers can be identified based on the similarity measures. Having larger distance, maybe outlier. Finding observations with large distances from all other observations. Graphic profile diagrams highlighting outlying cases. Their appearance in cluster solutions as single cluster, single member or small clusters. So they also may be outliers. Now, how to decide sample size? This is very important. And it is the sample size determination is very important in case of say medical sciences, biological sciences, where some ethics are involved. So maybe later on, Dr. Yadav will be organizing a separate workshop on sample size determination. But here we will have a little bit information about this sample size. The researcher should ensure that the sample size is large enough to provide sufficient representation of all relevant group of population. So we must take care of the sample size. So at least minimum sample size should be there to have, inference about the parameters under consideration. So the researcher must therefore be confident that the obtained sample is representative of the population. So it is very important that sample should be well representative of the population, and it must be of appropriate size. So that is sample size determination is very important sometimes for the statistical analysis or tests to be valid. Now standardization of the data is very important because we deal with the different type of variables with different say measures. So clustering variables that, and we cannot compare them if they are having different measures. So clustering variables that have scales using widely differing numbers of scale points or that exhibit large differences in standard deviation should be standardized. That is why we make them unit free. The most common standardization conversion is Z-score, that is standard normal score, with mean equal to 0 and standard deviation equal to 1. That standardization is done for all the variables under consideration. Deriving clusters, this is very important. There are number of different methods that can be used to carry out a cluster analysis. These methods can be classified as follows. There are basically three, mainly two, and if we combine the two, then the third one is the method of for deriving these clusters. The first one is hierarchical cluster analysis, another one is non-hierarchical cluster analysis, and if we combine the two, then we get the third one, that is combination of the two methods. Now we come to hierarchical cluster analysis. How hierarchical cluster analysis work? The stepwise procedure attempts to identify relatively homogeneous groups. Definitely here what we do on the basis of the similarity on the basis of all the characteristic under consideration. So homogeneous groups of cases based on selected characteristics using a algorithm either agglomerative or divisive, resulting to a construction of a hierarchy or tree-like structure that is known as dendrogram, which we have discussed, depicting the formation of clusters. This is one of the most straightforward method. So hierarchical cluster analysis are performed or preferred when the sample size is moderate, say from 300 to 400, not exceeding 1000. So we should keep this in mind that if the sample size is less than 1000, then we will go with the hierarchical cluster analysis. And if it is more than that, then we may go with the non-hierarchical cluster analysis. There we know in advance the number of clusters. Two basic type of hierarchical cluster analysis: agglomerative algorithm and divisive algorithm. So algorithm defines how similarity is defined between multiple member clusters in the clustering process. So how do we do this agglomerative algorithm? Hierarchical procedure that begins with each object or observation in a separate cluster. It means if we have say 2000 or say 200 observations or objects, then single object will make a cluster, and then we combine the two clusters on the basis of the similarity. So here in agglomerative method, what we do, we make the one cluster from many clusters. So this is many to one type of algorithm, and contrary to that, the divisive is from one to many. So in each subsequent step, the two clusters that are most similar are combined to build a new aggregate cluster. The process is repeated until all objects finally combine into a single cluster from n cluster to 1. This is many to 1. N cluster to 1. Similarity decreases during successive is definitely because we first combine the two units or say you two clusters with the least distance. Then we add the clusters with the higher, little bit higher distances. So here similarity is decreased as we move to further steps. So clusters cannot be split. We add. We split them into only into the Divisio algorithm. So Divisio algorithm begins with all objects in a single cluster, which is then divided at each step into two additional clusters that contains the most dissimilar objects. The single cluster is divided into two clusters, then one of these clusters is split for a total of 3 clusters and so on. So this continues until all observations are in a single member cluster. So this method is from one cluster to n subclusters. See here, this dendrogram, T-gram. So this method is Divisio and this is agglomerative. First we have added E to F at step 1, then this one, then this one and this one, then this one, this one. So this is known as agglomerative. Now come to Divisio. So we have taken this the whole as a single cluster, then we have splitted the first having the largest distance, and that is A. So first at first step we will divide this A, then this BCD, then with EFG, and then at next step B, C will be separated, and here E and F will be separated. So this way we can make single point clusters from one to many. Now agglomerative algorithm, among numerous approaches, the 5 most popular agglomerative algorithm are single linkage, complete linkage, average linkage, centroid method, Ward's method, and Mahalanobis distance. So one by one we will be discussing how these linkage methods are applied or to cluster analysis. Now come to single linkage. Single linkage means we take the closest points of the two clusters, and then this distance is known as the single linkage, because on the basis of the closest points we combine the two. So this single linkage, also called as the nearest neighbor method, defines similarity between clusters as the shortest distance from any object in one cluster to any object in the another cluster. So this is the smallest distance. So that is known as single linkage. Now come to complete linkage, the farthest points. So here it is farthest point of the one cluster and the farthest point of the another cluster, and we combine them. So this is known as the complete linkage. That is also known as the farthest neighbor method. Now come to average link. So every point is added to, we take the distance of every point of one cluster to every point of another cluster. So we start from say from here. So this one is distance of this point from this point to this point, from this point to this point. Then from this point to this point, this point to this point, this point to this point. Then from this to this one, this one, this one, and we take the average of all these distances. So the distance between two clusters is defined as the average distance between all pair of the two clusters members. Now we come to centroid. What we do centroid? We take the average of the points of the same cluster. Here we take the average of that and we combine the two. So this is known as centroid method. Cluster centroids are the mean value of the observation on the variables of a cluster. So this is the average of these points, of the cluster, and then combine to both of the average points. So the distance between the two cluster equals the distance between the two centroids So here we take the distance between the two clusters as the distance between the two centroids of the clusters. That is why it is known as centroid method. Now we come to Ward's method. The similarity between two clusters is the sum of the squares within the cluster summed over all variables. So on the basis of all variables, we take the observations, square of the observations, and we add them. Ward's method tends to join clusters with a small number of observations, and it is strongly biased towards producing clusters with the same shape and with roughly the same number of observations. This is the one of the biasness of the Ward's method. Now we come to hierarchical cluster analysis. The hierarchical cluster analysis provides an excellent framework with which to compare any set of cluster solutions. So here we don't know the number of clusters, only we try to make the clusters on the basis of the similarity. So this method helps to judging how many clusters should be retained or considered. So from hierarchical cluster analysis, we can have an idea that how many clusters should be formed. So now come to non-hierarchical cluster analysis. Here we have the number of clusters known in advance. So that is why what we do in cluster analysis, first we apply hierarchical cluster analysis to know the number of clusters. And once we know the number of clusters, then we apply this non-hierarchical cluster analysis with the known number of clusters, and we get the cluster analysis. Yeah. So now non-hierarchical cluster analysis, in contrast to hierarchical method or hierarchical cluster analysis, the non-hierarchical cluster analysis do not involve the tree-like construction process. Instead, they assign objects into clusters once the number of clusters is specified. So here we already know the number of clusters, so there is no need of dendrogram. So two steps in non-hierarchical cluster analysis: that specify cluster seed, what should be the cluster seed, where to start. So identify starting point, where to start. And then another step is assignment. First the starting point, then assignment of the observations. So assign each observation to one of the cluster seed. First, which you have decided that I will assign the unit to say cluster 1. So see which one is closer to that cluster 1. You start the seed and see the distance and assign the observation to that cluster. So we have to define the cluster seeds for the clusters of the consideration. So non-hierarchical clustering algorithm is sequential threshold method, parallel threshold method, and optimizing procedure. All of this belongs to the group of clustering algorithm known as k-means cluster, because here we have already in advance that k clusters and starting points are taken on the as the centroid, or seeds are taken as the means. So that is why it is known as k-means clusters. K-means method. This method aims to partition the n observations into k clusters, in which each observation belong to cluster with the nearest mean. Nearest mean, we take the centroid. So we have decided that we are going to make k clusters, say, and we have n observations. Obviously, n is greater than k. So we assign the observations to the nearest, to the mean. We calculate the centroid of the k clusters, and on the basis of the similarity, we assign the observations to that centroid points, to the clusters. So k means is so commonly used that the term is used by some to refer to as non-hierarchical cluster analysis in general. So many times we call this method as not as non-hierarchical cluster analysis. We say that it is k-mean cluster analysis. What are the advantages of hierarchical cluster analysis? Simplicity. With the development of dendrogram, the SCA hierarchical cluster analysis so afford the researcher with a simple yet comprehensive portrayal of cluster solutions. We can see the clear picture that how many clusters are should be made. Measure of similarity. Hierarchical cluster analysis can be applied to almost any type of research question. We can apply it to any research question. And speed, obviously, we make the dendrogram. Hierarchical cluster analysis have the advantage of generating an entire set of cluster solutions in an expedient manner. We can make all the number of possible number of clusters because we start from single member cluster to one. So we can have all idea how many clusters should be made. What is the disadvantage of hierarchical cluster analysis? That we don't have exact idea that how many clusters should be made and if there are outliers and they are important. So these are some drawbacks or disadvantage with the hierarchical cluster analysis. To reduce the impact of outliers, the researcher may wish to cluster analyze the data several times. Each time deleting problem observations or outliers. It is advisable, it is advised that if outlier is not of importance, then we should remove it from the analysis. And if you have removed, then you have to repeat it again for the rest of the observations, hierarchical cluster analysis, to see now what change will happen. So hierarchical cluster analysis is not amenable to analyze large samples. So it is, not very appropriate to handle with the large samples, because if say we have some outliers and then again we have made say cluster scatter plot and we are finding again some outliers. So it is very hard to deal with the every time you have to, if you have removed the outlier, then you have to again make the dendrogram, then again you have to make the dendrogram. So this is very tough to repeat the whole analysis for the every time you are removing the outlier. So it is very tough to deal with the large sample. Now, what is the advantage of non-hierarchical cluster analysis? The results are less susceptible to outliers because we already know, so somewhere it will be assigned in the data. The distance measure used and the inclusion of irrelevant or inappropriate variables. Everyone will be assigned somewhere. Non-hierarchical cluster analysis can analyze extremely large data sets because we already know the number of clusters. So every object will be assigned to the pre-decided number of clusters. Now these are some disadvantages as well, because if there are outliers, then we are assigning it to some clusters. So but so it may disturb the centroid point or like that, or any distance measure you are using. So even a non-random starting solution does not guarantee an optimum clustering of the observation because of the outliers or say extreme observation. In fact, in many instances, the researcher will get a different final solution for each set of specified seed points. If you are making different seed points and they are not very homogeneous to each other, then definitely we will have a different solution for different seed points. So this is a big drawback of this non-hierarchical cluster analysis. Now, non-hierarchical methods are also not so efficient when a large number of potential cluster solutions are there. So each cluster solution is a separate analysis. So every time we have to make different cluster solutions. In contrast to the hierarchical technique that generate all possible cluster solutions, it do not do that. It does not do that, because here in advance we have made the number of clusters, so there is no need of that dendrogram. We do not make that dendrogram, so we cannot have ideas that how many clusters should be made. If we are using 3, then we cannot have idea that we should make 4 or we should make 2. But in hierarchical cluster analysis, it is very clear picture that it gives the idea that we can make how many effective clusters. So this is the drawback of it. In contrast to the hierarchical technique that generate all possible cluster solution in a single analysis. Thus, non-hierarchical technique are not as well suited to exploring a wide range of solutions based on varying elements such as similarity measures, observations included, and potential seed points. If you are changing these any of the criteria, then solution will be changed. Now combining the both the method. So why we combine these two methods? First, to know the number of clusters, and then every observation will be used if we know the number of clusters in advance. So first, to know the number of clusters, we apply hierarchical cluster analysis, and once we know the number of clusters, then we apply non-hierarchical cluster analysis to assign every unit under consideration to the assigned number of clusters. A combination approach using a hierarchical approach followed by a non-hierarchical approach is often advisable. First, a hierarchical technique is used to select the number of clusters and profile cluster centers that serve as initial cluster seeds, centroid or any other, in the non-hierarchical process. So a non-hierarchical method then clusters all observations using the seed points to provide more accurate cluster numbers. So in this way, the advantage of hierarchical method are complemented by the ability of the non-hierarchical method to refine the results by allowing the switching of the cluster numbers. Now, how to interpret the clusters? This is very important. The cluster centroid, a mean profile of the cluster on each clustering variable, is particularly useful in the interpretation stage. Interpretation involves examining the distinguishing characteristic of each cluster's profile and identifying substantial difference between clusters. That is, we use the proximity or distance measure. So cluster solutions failing to show substantial variation indicate other cluster solutions should be examined. We should make some different number of clusters. We should examine that. So the cluster centroid should also be assessed for correspondence with the researcher's prior expectations based on theory or practical experience. So we should be very careful while choosing the centroids of the clusters. Validation of the clusters. Validation is essential in cluster analysis because the clusters are descriptive of a structure. As we say that this is the drawback of the cluster analysis, and require additional support for their relevance. Cross-validation empirically validates a cluster solution by creating two subsamples, randomly splitting the sample, and then comparing the two cluster solutions for consistency with respect to the number of clusters and the cluster profiles. So we can randomly split the cluster. Validation is also achieved by examining these differences on variables not included in the cluster analysis. So we can see the distance, how it is different from the variable which is included into the analysis, but for which a theoretical and relevant region enables the expectation of variation across the clusters. It is capable to discriminate between the or among the units, but it is not included in that cluster analysis. Now, how this cluster analysis is done in spaces, very quickly we'll see, and then we will be doing hands-on on that. So types of cluster procedure: hierarchical cluster analysis, and non-hierarchical cluster analysis, and then two-step cluster analysis. Hierarchical, say this is one example that this that one file is containing say 20 cases, each responding to items on demographics, say gender, qualification, days of absence from work, whether they smoke or not, on their attitudes to smoking in public places. Subtest total for pro and anti, plus total scale score for self-concept. We are attempting to determine how many natural groups exist and who belongs to which group, and on the basis of their attitudinal or attitude towards smoking in public place. So here, how we do this cluster analysis in SPSS, we go to analyze, then here go to classify, and then go to hierarchical cluster analysis. So the initial step is determining how many group exists. The SPSS hierarchical analysis actually calculates every possibility between every everyone forming their own group, single cluster, as many clusters as there are cases. We start from many to one, and everyone belonging to the same group, giving a range in our data from 1 to 20 clusters. So from 20 clusters, we make to one cluster. Now there go to method, and if you will click this, you click on plot, go to methods, every one by one, we will explore every option there. So go to plot, and there you click on the dendrogram. Then go to method, and then you can select the method here, Waltz method, or say some other method, centroid, or any other method, single linkage, complete linkage. So this way you can use it. So this Waltz method, and go to this interval as which distance measure you are using, Euclidean space or squared Euclidean space, you can select by your own, and then click on continue. So this dendrogram will be formed. So you can see here, there is a clear picture that this makes the one cluster, this makes the another cluster, and this makes the third cluster. So we can have idea, this dendrogram is showing that we should make 3 clusters. And if you think that it is having some another distance, then this may be considered as the outline. So this one, and this one, you can make the clusters. So on the basis of that distance, see here, these are the coefficients, and these are going to be last step. So you can see number of clusters. When there are 2 clusters, the change is of this quantity. When we are making 3 cluster, 4 cluster, 5 cluster, 6 clusters, so this way you can see that the distance is coming very low. A clear demarcation point seems to be here. See here, these are the two clusters which are having the distance as 1000, and these are having very close to each other. So this way we can have idea. This point may be taken as the point from where we can make the another cluster. So this way we can make these 2 clusters together, and this third one another cluster. So this way we can make 3 clusters, or we can make, if we are combining these 2, so then we can make 2 clusters. So a good cluster solution sees a sudden gap in the distance coefficient. Here, see, this is the change, and these are the distance coefficients. See the change, this one, see the change, this one. This way we can calculate. The solution before the gap indicates the good solution. Table this to 23.2 is a reform table to see the changes in the coefficient as the number of cluster increases. If there are 2 clusters, the change is this. From if we are making only 2 clusters, we are making 3 clusters, changes this. Making 4 cluster, changes this. So this is rapid, drastic change. The final column headed change enables us to determine the optimum number of clusters. In this case, it is 3 clusters, as the succeeding clustering adds very much less to distinguishing between cases. So here, this distance is considerable, this distance is considerable, change is considerable, but here we are having very lesser change. So this way we can make up to 3 clusters. Now you can go for the another options. You can have some number of clusters you can define. So repeat step 1 to 3, place cases into one of the 3 clusters. So this way we can make 3 number of clusters 3. So this way we can repeat for 2 cluster, 3 cluster. You can see for all number of places. Now you see this column has been added that these are the observations. So are the units say which unit is assigned to which clusters. So first one is assigned to first one, second one is assigned to second one, third one is assigned to first one, fourth one is assigned to third one. So this way we can see which object has been assigned to which cluster. A new variable has been generated at the end of your SPSS data file called cluster3_1. This labeled word method in variable view. That is word method. This provides the cluster membership for each case in your sample, which objects has been assigned where. So 9 respondents have been classified in cluster 2, while there are 7 in cluster 1 and 4 in cluster 3. So this way, all 20 are assigned to these 3 clusters. Now you can go for the option. You can here have one-way ANOVA, descriptive, and this way you can have many other statistics. So this way you can see which characteristic is going to be significant or non-significant, which is not contributing in discrimination. So you can see here qualification does not have significant contribution. All are significant except this qualification. So qualification did not produce any significant association because it is having the p-value as very much greater than 0.05. Now, how to interpret the clusters? Cross-tab analysis of the nominal variables, gender, qualification, and whether smoke or none or not produce some significant association with clusters. So this way we can, this classification column is word lib method, and we have these 3 another categorical variables, that is gender, and this one is smoke or not, and then we can have cross tab. So go to analyze and go to cross descriptive, then cross tab. So we can have idea that whether these are independent to these groups or not. See here, cross tab, gender, male, female, and these are the word method means we have 3 groups, 3 cluster 1, cluster 2, cluster 3. So you can have that male are 6 males are in cluster 1, 8 in cluster 2, and 1 in cluster 3. So 15, this 5, 10, and this way. Now we come to this is another characteristic, that is smoke towards these. So you can have idea that 13 are in non-smoker group, 13 are here, and smokers are 7. So they are distributed as 0, 3, and 4. So 0, there are no smokers in cluster 1, and while there are 3 in cluster 2 and 4 in cluster 3. So this way we can have cluster consist of male. So we have made these 3 clusters as cluster 1. We have named it as consist of male non-smokers. Cluster 2 consists of smoking and non-smoking males. And this one consists of smoking females only. So you can see that there are 4 female smokers and there are no female smokers. So all females are smokers in 4 females which smoke. So here this is the descriptive statistics. You can have idea that how many numbers are. So we have defined these 3 clusters as these consist of male non-smokers and consist of smoking and non-smoking males and another smoking females. So this way you can have idea for all. So you can how many non-smoking male, smoking males and smoking females. So this way you can have idea for self-concept score. And these are the mean score, these are the standard deviation, this is standard error for the mean, and these are 95% confidence interval, these are maximum emission. So these are for all the characteristics, say self-concept score and days absent last year, and all the on the basis of all characteristics we can have decide. So cluster 1 is characterized by low self-concept, average absent rate, average attitudinal score to anti-smoking, non-smoking males. So these are characteristics for the for cluster 1. And for cluster 2, we can have it's characterized by moderate self-concept, low absent rate, average attitudinal score to anti-smoking, smoking and non-smoking males. So cluster 2 will be made this way. And third one, it characterized by high self-concept, high absent rate, low score to anti-smoking, smoking females. This one is the third class. Now we come to K-means cluster. So it is, already well known in advance the number of clusters. So how we'll apply? Go to analyze and go to classify. There you will see K-means cluster. Click on that, you will see the maximum minimum number of iterations 20 and convergence criteria 0, no issue. And we have to make the number of clusters in advance. So this is 3. You will see, go to statistics. So initial cluster centers, we need, what table we need, cluster information for each cases we need. So click on continue and then statistics, it will show the information for each group. It is very important to know in non-hierarchical cluster analysis to the starting points. That is cluster seed and number of clusters. So you can see here, these are the 3 clusters and these are assigned on the basis of these characteristics. These are the distances, say. The initial cluster centers, these are the cluster centers for the characteristics. The initial cluster centers are the variable values of the K well-spaced observations. These are the mean centroids of the clusters for different characteristics. For cluster 1, cluster 2, how this will measure from this point, this characteristic will measure from this point. So this way we can calculate these. Now iteration deals with the misclassification. Actually, the iteration history shows the progress of the clustering process at each step. So this way we can have some idea that we can move value from one to another. See, in early iteration, the cluster centers shifted quite a lot. So cluster centers are shifted from one point to another. So you can see for clusters, for different all characteristics 18 say. And now by the 14th iteration, so this is iteration 1, 2, 3. For iteration 1, these are centroid, say centroid or seed points for 3 clusters. For step 2, so you can see here it is 3.2, and in step 2 it is 1. It is 3.4, it is 0.4. So there is drastic change. So you can see here, and after that, if they are not changing, then we can have idea that we can make these seeds for the starting. So by the 14th iteration, they have settled down to the general area of their final location. And the last 4 iterations are minor adjustment. So that is why you see 0.000. So this is that is why it is very important to know the consistent observation as the centroid or the seed point for the nanometer. So that is why we take the number of iterations. You can see this is the ANOVA. The ANOVA table indicates which variable contribute the most to the cluster solution. So all are significant. All are contributing significantly. That p values are very much less than 0.05. So variable with large f values provide the greatest separation between clusters. So if here p value is significant, so here we can have idea of p. So, sorry, f is statistic. So larger the value of x, larger the contribution in separating the observations or objects. Now here this is cluster 1, cluster 2, cluster, and as the point center point changes, so the position of the clusters changes. These are the cluster centers. So this is a final cluster center. Final cluster comes from this iteration when the changes are almost consistent. The final cluster centers are computed as the mean for each variable within each final cluster. So if you have made the final clusters, then you take the mean of that. Yeah, mean of that. Yeah, mean of that. The final cluster centers reflect the characteristics of the typical case for each cluster. Then it will reflect the center for that particular cluster. So customer in cluster 1 tend to be big spender who purchase a lot of services. This way you can see the value. So on the basis of that, we can discriminate among the customers or objects. Say customers in cluster 2. See this one. So here, if you take the average of that, you will have moderate, little bit large value. If you will take the average of these centers, then you will see that it is going to be lesser than that, and this is going to be least among these 3. So this way we can have idea. The customer in cluster 2 tends to be moderate spender who purchase the calling services, and while in this customer in cluster 3 tends to spend very little and do not purchase many services. So you can have average of that it is least among these 3 clusters. So this way you can have idea of cluster 1, cluster 2, and cluster 3. So you can discriminate among these. Distance between final cluster centers, you can have the idea that is average of that. This table shows the Euclidean, this shows that Euclidean distances between the finest cluster centers. So we have 3, say, final cluster centers. Then we can have idea of that. You take the Euclidean space, square root of the distance for every characteristic, get the square of that, and take the sum, and then get the square root of that. So you will have the this for cluster 1, cluster 2, cluster 3, you can have. So by taking the centroid average of that. See here, take the average of that, and take the distances for every characteristic. Then you can have, and take the square root of that, then you can have these distances, Euclidean distance. That is distance between the final cluster centers. Greater distance between cluster correspond to greater dissimilarity. So obviously it should be high, then it will make the difference between the clusters are among the clusters. Cluster 1 and 3 are almost are most different. Just see here that Euclidean distance between cluster 1 and 3, say 1 and 3, it is 4.8, highest distance. Between 1 and 2, it is 3.45. And between 2 and 3, it is 3.3. So these two and 3 are very close to each other, but 1 is different from 3. So this way we can have. Cluster 2 is approximately equal, similar to the cluster 1 and 3. This here, this one and this one. But 1 and 3 is different. 1 and 3 is having highest distance. So it is different from that. See here, this one. Number of cases in each cluster. Total 1000 is divided in these 3 clusters. So this is having a big group, almost having 500 persons. A large number of cases were assigned to the 3rd cluster, spending least one, which unfortunately is the least profitable group. So perhaps the 4th more profitable cluster could be extracted from the basic services group. This. So if we are now, if we are making 4 clusters, then this will be splitted in that. So very quickly we see, if it is 4, then finally we can see here that. Okay, now in 3rd, it is 212 and 280 are in 4th. So this tells about that we can make the, as per our profit, say as per our requirement, we can make the, we should make number of clusters 4. The 2-step is that just first apply that, I mean hierarchical cluster analysis, then non-hierarchical cluster analysis. So this is this we can go to classify, then go to analyze, classify, and then you will see here that see which is written here. 2-step, that is 2-step cluster analysis. So go to that and you can apply. So you can see this way. So this was today's discussion about the cluster analysis. Now, after a 5-minute break, we will be doing hands-on, and then after that, we will be entertaining the questions one by one. So let us take a 5-minute break, and after that, we will be discussing. We will be doing hands-on and then taking the questions, queries from the audience. Okay, we have a case study that we consider a clustering of customers based on attitudes towards shopping. Based on past research, 6 attitudinal variables were identified. Customers were asked to express their degree of agreement with the following statements on 7-point scale. 1 is strongly disagree and 7 is strongly agree. And these are the questions, that 6 questions, that I love to buy products in shopping mall. I buy discounted products. I enjoy eating food at shopping malls. I bargain products when shopping. I buy only daily need products, and I compare price of products in shopping malls. So let us see how many clusters will be made. So we have this data. Okay. So we have these, I mean, 6 questions that see here. I love to buy products in shopping mall this way. So all are numeric because we have taken the data in 7-point scale, and just come to this. So we have taken observation on 25 persons. So now how to analyze it? Now go to analyze, then classify, and go to hierarchical cluster analysis. So you put all the variables here. Okay. Now go to statistics, agglomerative and prox. If you need, then you can have a proximity matrix as well. And click on continue. Then go to plot. So this is very important that we should check this dendrogram. Click on continue, then go to method. So you can see between group linkage, or you can say we should use this Watts method and squared Euclidean distance, or you can use Euclidean distance or say squared Euclidean distance. And then click on okay. Standardization is already given there, and just click. Say we need the plot as well as statistic. So just click on OK. So this is the proximity matrix from every point to every point distance, and there is no, I mean, very much need of it. So you can see here, this is the case processing summary. 25 persons are there and all are present. And this is agglomerative schedule. You can see here, this is cluster 1, cluster 2. Already there are 2 clusters only. And you can see through word linkage, you can see this is cluster combined, and this is stage cluster. First appears cluster 1, cluster 2, you can see here, and how the points are added to. These are the coefficients. On the basis of the coefficient, you can see here how they are added to each other. So first step, second step, then next step. So through every stage you can add them. This is the dendrogram you can see here. So from this we can have idea that we can make the 3 clusters. While there it has made only 2 clusters. You can see here this one and this one. But we can separate it as the third one, first one, second one, third one. So this way we can make. So you can have idea of 3 clusters as well. But here it has given the idea about the 2 clusters. Now we can make the 3 clusters. From here we can have idea. So now let us do the non-hierarchical cluster analysis. Go to analyze and go to classify, then go to k-mean cluster. Okay. So here you put select all the variables and put them here. Okay, go to number of iteration 20. You can put here 20. Okay, then go to save. So now cluster membership is very important. This distance you can say from cluster center, you can also have a distance, idea of distance. So 2 variables will be added in data, and number of clusters, suppose we are making 3. Then just click on OK. You can go for the options as well. Now go to ANOVA table, initial cluster centers, and ANOVA table are you can, okay, we need both. Just click on OK. So you can have, these are the 3 clusters. These are initial cluster centers. From where to start? This is iteration history. There are only 2. And you can see here, these are the final cluster centers, and then we can have average of that to make the distances. This is ANOVA. You can see here every characteristic, all 6 questions are important. They are, I mean, significant in contributing in classifying the customers. Now, this is the number of cases in each cluster. So you can see here we have taken 25 customers. So in first cluster, there are 8 customers, then 10 customers and 7 customers. So on the basis of these, say values, you can have idea. You take the average of that, and you can give the name to the clusters on the basis of the average of that. So this way we can have the idea of hierarchical cluster analysis. So this was all about today's discussion. And if you wish to have, I mean, see here, this class membership has been added, and these are the distance measures from the center points. So see here, the first customer has been added to second cluster, third cluster, first cluster. This way, all the customers are classified into different clusters. Now suppose now we are removing these the 2 columns, and if you wish to go analyze, then go to classify, and then 2-step cluster. We have no say categorical variables, so you put all the continuous variables here, and you go to option. Okay. Output you can have output variable, or say pivot table charts you need. Okay, then just click on OK. So this way you can see these 3 clusters may be made, this one, and this one. So it is good to, I mean, use that first hierarchical and then non-hierarchical cluster analysis, and you will get the number of cluster membership as well as the centroid and distance from all clusters, cluster points, cluster centroids. So this was all about today's discussion. Now, if you have any query, any question, please ask.
Thank you so much, sir, for your very informative session. Now the participants can unmute themselves and ask any questions if they have.
Hello, sir.
Yeah.
Please provide the recorded session of how to download the SPSS trial version.
Okay, we will provide the link. If you have any query regarding today's session, please let us know.
Okay.
Sir, can you please tell once more how you interpreted the tree as in the last example as 3 clusters are possible instead of 2?
On the basis of the dendrogram.
Yeah.
You can have idea that the similarity, you will see the units of the similarity of the units. So through agglomerative method, we can have idea to make the 3 clusters through dendrogram.
Sir, could you just show it with the diagram, with the dendrogram, how you decided 3 are
I have
possible?
shown, I think you have missed, but let me do it again. Let me do it again. So I will be doing it. Yes, see ma'am, go to analyze, then go to classify, and we are using first the hierarchical cluster analysis. You put all the variables here and go to statistics. You will see we know this agglomerative schedule, and okay, click on continue, then go to plot. We need this dendrogram. Okay. Again, go to method. Here you can select this word method as well, and squared is okay. And you can apply a standardization if you wish from 0 to 1. Otherwise, you leave it. Click on OK. And if you wish to see this, which we need cluster membership, single solution, or say none, say single solution. So then you have to make the number of clusters, but we wish to know how many clusters we should make. So cluster membership, no, there is no need. So just no need it, cancel it. And now we need to display this statistics as well as the plot, that is dendrogram. Just click on OK. Now directly we come to this dendrogram. So you can have idea from this that this is suggesting that we should make two clusters. This one is and this one. These two clusters are added at last. But you can have idea from here that this group is making one cluster and this group is making another cluster, and this one is third cluster. So this clearly shows that we should make 3 clusters instead of 2 clusters. So that is why I have made 3 clusters.
Okay, so that is depending on the number of units that are there in each cluster.
Close to each other. So
Okay.
this cluster, actually we have added these 4 units. Then this unit has been added with this one. But this cluster is, distant from this cluster. So it has been added, but this is distant from that. So see here, there are 3 clear picture. One, this one, another this one, this one. At last, this one is added with this one. So we have 3 actually, this cluster, and this cluster. So we can have idea that we should make 3 clusters here.
Okay, sir. Thank you.
So I think there are no more questions from the participants. So thank you so much, sir, for very informative and very elaborative session. So we'll meet tomorrow. Thank you all the participants for your patiently listening. Thank you all.
Right.